Let us see the concept of reflection of wave. Transverse waves incident on a surface between the two boundaries. For example, this is one medium, this is second medium. This light ray, or sorry, in this case, this wave is incident on interface of the two media. When sound wave incident on the interface of two media, a part of this incident ray reflection takes place into same medium, reflects back into same medium. A remaining part of wave, out of that partly absorbed, partly transmitted. That means when incident wave, when a wave is incident at the surface interface of the two media, partly reflected, remaining part, in the remaining part, some part is absorbed by this second medium and remaining part is transmitted or refracted into the second medium. So in this case, this is incident wave which makes an angle I with the normal. The angle I is the incidence, reflection, refraction, all these angles always measured with respect to normal. Where I is the angle of incidence, this R is angle of reflection, R dash is angle of refraction. So here reflected wave pulse, this is reflected wave pulse, the refracted wave pulse. See, angle I, angle R both are equal. That is, angle I is equivalent to angle R based upon one the angle of reflection. Now, this is refracted ray, refracted ray. Reflected ray, refracted ray are mutually perpendicular. According to Snell's law, which we use in optics, even here also we can apply that. Sin I by sin R dash, where I is the angle of incidence, R dash is angle of refraction. Sin I by sin R dash is equivalent to Vi by Vt. That means it is the ratio of V means a speed of wave in the incident speed, incident wave. Vt is the speed of refracted wave. So here, when a light ray or sound wave passing from one to another medium, only one physical quantity remains is frequency. Speed may change, lambda may change, so frequency remains. So in this way, reflection of waves, we have two types of waves. One is called transverse wave, other is called. So reflection of wave depends upon the nature of boundary where the reflection takes place. So we have transverse waves, other is called longitudinal pressure waves. When transverse pulse, this is the transverse pulse incident on the fixed boundary. Reflection of waves can be explained in two cases. Reflection of waves from the free boundary, reflection of waves from the fixed boundary at the fixed end. Suppose say this is the rigid end, this is the rigid end. This is incident pulse, this is incident pulse. When reflection takes place from rigid end, this is how the wave is reflected from the rigid end. So here, when transverse pulse is incident at the rigid end, so what let us see one example. This is the crest of the transverse wave incident at the rigid end. When the reflection takes place from rigid end, what happens here? Crest reflects as a trough. If it is trough, this will become crest. That means, in the case of transverse wave, when the reflection takes place on the fixed end or the rigid end, crest reflects as a trough, trough reflects as a crest. Therefore, the phase difference between them is equivalent to pi radians. I repeat again, in the case of transverse pulse, when it is incident on the rigid end, if the crest incident no, reflection takes place as a trough. If trough incident no, reflection takes place as crest. So crest as a trough, trough as a crest. So therefore, the phase difference between them is pi radians. In the case of longitudinal pressure waves, from the rigid end, compression reflects as compression, rarefaction reflects as rarefaction. In this case, delta phi is equivalent to 0 radians. That means, so when the reflection takes place from the rigid end, in the case of transverse pulse, crest reflects as a trough, trough reflects as a crest. Phase change is pi radians. In the case of longitudinal pressure waves, compression reflects as compression, rarefaction reflects as a rarefaction, delta phi is equivalent to 0 radians in the case of rigid end. Similarly, when the reflection takes place from the free end, in the case of free end, what happens? If this is the incident pulse, this is incident pulse from the free end, reflection takes place in the free end, again this will be reflected pulse. That means for transverse waves, when the reflection takes place from the free end, crest reflects as crest, trough reflects as a trough, therefore the phase difference between them is equivalent to 0 radians. In the case of longitudinal pressure waves, when the reflection takes place in the free end, compression reflects as rarefaction, rarefaction reflects as compression. In this case, phase difference delta phi is equivalent to pi radians. So I repeat again, once again concentrate, listen. When the reflection takes place from the free end, in the case of transverse wave, crest reflects as a crest, trough reflects as a trough. The phase difference between them is equivalent to 0 radians. In the case of longitudinal pressure waves, when the reflection takes place from free end, compression reflects as a rarefaction, rarefaction reflects as a compression, the phase change is equivalent to pi radians. So let us see, when a wave is propagating from rarer to denser medium or denser to rarer medium, how the reflection takes place, how the transmission takes place. Let us see, the wave pulse is propagating from rarer to denser medium. Let us see, this is the crest of incident pulse. This is rarer, this is a denser medium. The transmitted pulse is like this. After reflection, this is what we call reflected pulse. Crest reflects as a trough. See, we know incident pulse displacement Yi is equivalent to Ai, where Ai is the amplitude of incident pulse, A sin omega t minus k1x. So, after reflection, Ar is the amplitude of reflected pulse, sin of omega t minus k1 of minus x plus pi, because as we discussed just now, when the reflection takes place from the fixed end, the phase change is equivalent to pi radians. Crest reflects as a trough, trough reflects as a crest. Therefore, Ar sin omega t minus k1 of minus x plus pi. This is what we call reflection, after reflection, displacement of reflected wave. Therefore, Yr is equivalent to minus Ar sin omega t plus k1x. We discussed already, when a wave is propagating along the x-axis, y is equivalent to A sin omega t minus kx. The wave is propagating along negative x-axis, y is equal to A sin omega t plus kx. Similarly, incident pulse is Ai sin omega t minus k1x. Reflected pulse is Ar minus Ar sin omega t minus k1x. But transmitted pulse, this is transmitted pulse. In this case, At amplitude may change, sin of omega t minus k2x. When a wave is propagating from one to other media, speed changes, lambda also changes. Therefore, we know the formula k is equivalent to 2 pi by lambda. Due to change in lambda, now propagation constant will become k2. Therefore, Yt is equivalent to A sin omega t minus k2x. Therefore, when a wave pulse is propagating from rarer to denser medium, incident wave pulse is Ai sin omega t minus k1x, and reflected pulse is minus Ar sin omega t plus k1x, and Y transmitted is At sin of omega t minus k2x. Now let us see, when this sound wave pulse is propagating from denser to rarer medium. In this case, this is the incident pulse. After reflection, what happens here? This is what we call denser medium, rarer medium. If you look at the figure clearly, in this case and in this case, in both the cases, transmitted pulse is never inverted, but the incident pulse may be inverted. So let us see, when a wave pulse is propagating from denser to rarer medium, y is equivalent to a sin omega t minus k1x. Reflection takes place from free end. So in this case what happened? No phase change. Phase change is equivalent to 0. Therefore, a sin omega t minus of k1 minus x plus 0. Therefore, a r sin omega t plus k1x. So instant pulse is a sin omega t minus k1x. Reflected pulse is a sin omega t plus k1x. Why we do k1 over here only? Because in this case wavelength will not change. In the case of transmitted pulse, this will become a sin omega t minus k2x. As we discussed earlier, when a wave pulse is propagating from one to other medium, speed changes, wavelength changes, but frequency remains. So in this case, as the lambda value changes, y transmitted become at sin omega t minus k2x. This concept is useful for us in the concept of standing wave phenomena. Let us see superposition of waves. When two or more waves are traveling in the same medium, superpose each other, then the resultant displacement of those waves is equal to the vectorial sum of the displacements of individual waves. That means, if two or more waves are superposed one upon the other, the resultant displacement of resultant wave is the vectorial sum of their individual displacements. So for example, we have many waves whose displacements are y1 x1 comma t, y2 x2 comma t, etc., etc. When they are superimposed each other, the resultant displacement of the resultant wave is vectorial sum of the individual. That is, y of x comma t is equivalent to y1 x comma t, y2 x comma t. We have to add vectorially. That will give resultant displacement of the superposition of the waves. For example, there are two waves whose y1 is equivalent to a1 sin omega t, y2 is equivalent to a2 sin omega t plus phi. When the two or more waves are moving in the same medium, for example, they should have nearly same amplitude, they have same frequency. When they are moving along the same direction or opposite direction, they may have zero phase, they may have constant phase. Like that, they can superimpose one upon the other. Now in this case, let us consider y1 is equal to a1 sin omega t, y2 is equal to a2 sin omega t plus phi. These two are superimposed each other. When they superimpose each other, the resultant amplitude of these two waves is a net is equivalent to a1 square a2 square, because we know parallelogram law. Resultant magnitude is p square plus q square plus 2pq cos theta. Using the same formula, here a1 a2 are the amplitudes of two waves. Between these two, phi is the phase difference. When they superpose each other, the resultant amplitude of the so formed wave is a net is equivalent to a1 square plus a2 square plus 2a1 a2 cos phi. And the phase difference between them is tan phi, not between them, resultant wave and one of them is tan theta is equal to a2 sin phi by a1 plus a2 cos phi. Here, we know that intensity proportional to square of amplitude. So, a net a square net is equal to a1 square plus a2 square plus 2a1 a2 cos phi. This can be written in terms of I as I net is equivalent to a1 square can replace by I1, a2 square can replace by I2, I1 plus I2 plus 2 root I1 I2 cos phi. So this is the general formula to find out the intensity. This is the general formula to find out the amplitude. Now let us see constructive and destructive interference. Interference is nothing but superposition of waves only. What do you mean by constructive interference? Actual interference is nothing but the modification of intensity due to superimposition of two or more waves is what we call interference. Here we have two types of interference. One is called constructive, other is called destructive interference. Constructive is nothing but if the crest of one wave fall upon the crest of another, or trough of one wave fall upon the trough of another, that will use constructive interference. If the crest of one wave fall upon the trough of another, or trough of one wave fall upon the crest of another, that will use destructive interference, indicates maxima, minima, etc. Similarly, when I is equivalent to I1 plus I2 plus 2 root I1 I2 cos phi, this whole value to be maximum, means cos phi value should be maximum. If cos phi is equivalent to 1, then this value become I1 plus I2 plus 2 root I1 I2, which is nothing but I maxima is equivalent to root I1 plus root I2 whole square. That is possible when cos phi is equivalent to 1, when phi is equivalent to 0, and 2 pi, 4 pi, 6 pi, 8 pi, so on, so on, so on. So if it is 2n pi, this cos-phi value become 1, then this I net value become maximum as root I1 plus root I2 whole square. That is what you call maxima intensity. And for minimum this cos-phi value must be equivalent to -1 if it is. If this value become -1, what happens here? This value become -1, I minima can be replaced by root I1 minus root I2 whole square. When this value become cos-phi value is -1, I net value become I1 plus I2 minus 2 root I1 I2, which is equivalent to root I1 minus root I2 whole square. That means I maximum is equivalent to root I1 plus root I2 whole square, and I minimum is equivalent to under root I1 minus root I2 whole square. Let us say this is one wave which is moving upward direction. This is one more wave moving in downward direction. Suppose amplitude, this is called amplitude of two waves whose amplitudes are A1, A2. They are moving in opposite in direction. So if A1 is more than A2, this could be resultant wave whose amplitude is A1 minus A2. Similarly, this is one wave whose amplitude is A1. One more wave moving along the same direction whose amplitude is A2. They superpose each other. The resultant amplitude of these two waves will be like this, which is equivalent to A1 plus A2. This is maximum value, this is a minimum value. When A1, A2 both are equal, here in this case A maximum value is equivalent to A1 plus A2. In this case A minimum value is equivalent to A1 minus A2. So when two waves of amplitudes A1, A2 superpose each other, when they are moving along the same direction, resultant amplitude of resultant wave is A maxima is equivalent to A1 plus A2. When they are moving opposite in direction, resultant amplitude of the resultant wave is A minima is equivalent to A1 minus A2. So here if A1, A2 are the amplitudes of two individual waves, then A maxima is equivalent to A1 plus A2 and A minima is equivalent to A1 minus A2. So here we know that intensity proportional to square of amplitude, nothing, which is also equivalent to A proportional to root I. To find out the I1 by I2 ratio, I1 by I2 is equivalent to A1 square by A2 square. When amplitudes are given, to find out the intensity ratio, we can use I1 by I2 equal to A1 square by A2 square. When intensities are given to find out the amplitudes, we can use I1 by I2 is equivalent to A1 by A2 is equivalent to under root of I1 by I2. Similarly, I maxima to I minima ratio. Here I maxima proportional to A square maxima, which is nothing but A1 plus A2 whole square, and I minima proportional to A square minima, nothing but A1 minus A2 whole square. Now the ratio of maxima to minima intensity is I max by I min is nothing but A max by A min square. A max is nothing but A1 plus A2 by A1 minus A2 is A min square, which is also equivalent to A value can also replace by root I1, A2 can replace by root I2, this A1 can replace by root I1, A2 can replace by root I2. So this formula is important, which is related in terms of amplitude versus intensity. I max by I min is equivalent to A square A max by A min square, A maxima A1 plus A2, A minima A1 minus A2. This can also be in terms of intensity as root I1 plus root I2 by root I1 minus root I2 whole square. So let us see an example problem. Y1 is equal to 3 sin 2 pi t, Y2 is equal to 4 sin 2 pi t plus pi by 2, Y3 is equal to 5 sin 2 pi t plus pi. So each these two successive waves are differ by phase difference of pi by 2. That is between y1, y2 they are differ by phase difference of pi by 2, y2, y3 differ by phase difference of pi by 2, y1, y3 differ by phase difference of phi. We need to find out the net amplitude or resultant amplitude. Suppose this is phi sin 2 pi t plus phi, which is equivalent, this is equivalent to y3 representation, and here 3 sin 2 pi t between y1, y3 phase difference is equivalent to pi. If you take y1 downwards, y3 could be up. Now y2 is in between, that is if you represent y1 along this, y3 could be upward direction, because between y1, y3 phase difference is equal to pi radians. y2, y3 phase difference again pi by 2 radians. So here y3 is 2 pi t, phi sin 2 pi t plus pi. Now when you take the amplitudes, the amplitude of the y1 is equivalent to, this is 3, these are amplitudes, and for y3 this amplitude is equivalent to 5, the second one amplitude is equivalent to 4. As 5 and 3 are quite opposite, between these two angle is equivalent to 180 radians. So here the resultant of these two 5 and 3 will be acting upward. 5 minus 3 is equivalent to 2. Resultant amplitude of y1, y3, and amplitude of y2 is 4. These 2 and 4 are at an angle 90. The resultant of these two acting along this, which makes some angle phi. So the resultant amplitude is A net is equivalent to 4 here 2, 4 square plus 2 square under root, as angle between these two is equivalent to pi by 2 radians. So 16 plus 4 is equivalent to root 20 is equivalent to 2 root 5 is the net amplitude. Now direction, tan phi is equivalent to this by this. This is equivalent to 2, this is equivalent to 4. So tan phi is equivalent to 4, 2 by 4, phi is equivalent to tan inverse 1 by 2. So this is the method to find out the resultant amplitude of when 2 or more waves are given. Let us see one problem. 3 waves each of amplitude A. All the 3 waves have same amplitude. They have time period t. They are traveling out from a common point. So this is the point, from this point all these 3 waves are traveling out. The starting timings are, means initially the first wave travels out from the point O at beginning 0 time. After t by 3 seconds, one more wave is coming out of the same point. After 2t by 3, one more wave is coming out of the same point O. Now he is asking us to find out the A net value. I repeat again, the starting timings of them are 0, t by 3, 2t by 3. Suppose this is the point of O from which the waves are coming out. This is the first wave y1. After time of 2t by 3, after time of 2t by 3, this is second wave. What could be displacement of second wave after time of t by 3? We know y is equal to a sin omega t, that is the first one. Second wave is y is equal to a to a sin omega t phi. Here phi is nothing but a phase, no? So phi value, we have one formula, delta phi is equivalent to 2 pi by capital T into small t. This relation of phase and time relation. To delta phi is the phase difference, delta t is the time difference. Now in the problem he gave the time, we need to convert that in terms of phase. So what to do here? A sin omega small t plus 2 pi by capital T into t by 3, because the second wave is coming out of the same point after time of t by 3. So in place of small t, substituting t by 3, so here t gets cancelled, omega t plus 2 pi by omega t plus 2 pi into t gets cancelled, 2 pi by 3, that is second wave. And third wave comes out of the same point after 2t by 3, after this, that means 4t by 3. So on the whole what happens here? Omega t plus 2 pi by capital T, after 2t by 3 time it is coming out of O. This will become a sin omega t plus pi by 3. Means first wave coming at 0 time, after t by 3 is y2, After one more t by become after 2t by 3 is y3. Now these are the three waves y1, y2, y3. Here y1, y2 are differ by a phase difference of 2 pi by 3 is 120 degrees. y2, y3 differ by phase difference of 2 pi by 3, 4 pi by 3. Between these two phase differences again 120. We know y2 amplitude is A because all they have same amplitudes y1, y2, y3 A only. The resultant amplitude of y2, y3 is acting along the diagonal which is equivalent to A. We know that when two vectors of equal magnitude are inclined at 120 with each other, resultant of them is equivalent to either of them in magnitude. Therefore, y2 is A, y3 also A, angle between these two is 120, resultant of y2, y3 is A. And finally, we have result amplitude of y1 is equal to A, resultant amplitude of y2, y3 is equivalent to A. These two acting opposite direction, the A net value become 0. Therefore, the resultant amplitude of these three waves become 0. So, stationary waves or standing waves. When two set of longitudinal or transverse waves moving in opposite in direction, having same amplitude, same wavelength, same frequency, superpose each other, as a result standing waves are formed. That means when a wave is travelling along the positive x-axis, reflection takes place in the rigid end, that will travel opposite in direction, superpose standing wave is formed. That means standing waves or stationary waves both are same. That is possible by superimposition of two progressive waves travelling in opposite in direction. They interfere, as a result standing waves or stationary waves are formed. Let us see, this is one progressive wave travelling along the positive x-axis. This is rigid end, reflection takes place from here, this will move opposite in direction, as a result standing wave is formed. Otherwise, this is the free end, the wave is travelling like this, reflection takes place from the free end. Due to reflection, the reflected wave will travel opposite in direction, in this case also standing wave is formed. So here, this is one travelling wave moving along the positive x-axis. This is one more wave, reflection takes place like this, due to superimposition of the standing wave is formed. This is the free end, the wave is moving like this, reflection takes place from free end, due to reflection of this wave, standing wave is formed. Or one wave is travelling like this, one more wave moving in opposite in direction, interfere, then also standing wave is formed. This is one wave travelling like this, one more wave travelling like this, they superimpose, then also standing wave is formed. Therefore, standing waves are formed due to reflection takes place from a free end or a fixed end by same wave, or due to superimposition of two similar progressive waves travelling in opposite in direction, then also standing waves are formed. Let us see one wave y1 is equal to a sin omega t minus kx travelling along the positive x-axis, y2 a sin omega t plus x travelling along the negative x-axis. They superpose each other. Due to superimposition of them, resultant displacement is y is equal to y1 plus y2. So, taking a as common from this one, sin something plus sin something. In what form this is? Sin c plus sin d. We know the formula for sin c plus sin d, 2 sin c plus d by 2 cos c minus d by 2. Using that formula, this can be simplified as 2a sin omega t minus kx plus omega t plus by 2 cos omega t minus kx minus omega t minus kx by 2. After simplification of that, we will be getting 2a sin omega t cos kx. So, 2a cos kx sin omega. This is in what form? Y is equal to something sin form. This also represent a wave. So, y is equal to 2a cos kx. In place of 2a cos kx, what are we obtained? No, that is nothing but a amplitude of stationary wave. Therefore, a sin y is equal to a sin omega t. A sin omega t equation of this wave, whereas a is equivalent to 2a cos kx is the resultant amplitude of stationary wave. So here in 2a cos kx, no, there is no time, only displacement x is there. Therefore, amplitude of stationary waves varies periodically with position, with the displacement, not with the time. Now let us see condition for obtaining nodes, condition for obtaining antinodes. Displacement of amplitude of the stationary wave is 2a cos kx is equal to 0 for nodes. Nodes are the points which lies on equilibrium whose displacement is equal to 0 or whose amplitude is equal to 0. So this value equal to 0. So here as amplitude. So here k into x 2n minus 1 pi by 2. This cos kx value must be equivalent to 1. Sorry, cos kx value, I repeat again, 2a cos kx is equal to 0. In place of kx, when we have 2n minus 1 into pi by 2, this value becomes 0. Therefore, k is equal to 2 pi by lambda, we know, wave number or propagation constant, into x is equal to so and so. Simplification of this, x is equal to 2n minus 1 lambda by 2, lambda by 4. When n is equal to 1, 2 into 1 minus 1 lambda by 4, lambda by 4. N is equal to 2, 3 lambda by 4. N is equal to 3, 5 lambda by. That means from the initial point at a distance of lambda by 4, node is obtained. At a distance of 5 lambda by 4, from here 3 lambda by 4. This is lambda by 4. This is lambda by 4, lambda 3 lambda by 4. And again one more is at 5 lambda by 4, nodes are obtained. Now condition for antinodes. Displacement or amplitude of stationary wave 2a cos kx, this value must be maximum. Cos kx value must be plus or minus 1. So kx value must be n pi. So k is equal to 2 pi by lambda into x as it is over here. X is equal to 0, lambda by 2, lambda 3 lambda by 2. Means from here at a distance of 0 means in the beginning only we have antinode. After a distance of lambda by 2 means from here to here again antinode is obtained. Again at 3 lambda by 2 again over here antinode is obtained. So from this we can say this is the free end where antinode will form. Node forms at a distance of lambda by 4 from this position. Again next successive antinode is antinode to antinode distance is lambda by 2. Therefore, the distance between two successive nodes, two successive antinodes is lambda by 4, sorry lambda by 2. Node to antinode or antinode to node is lambda by 4. This is how the two waves are superimposing, which are travelling in opposite in direction. So standing waves are formed due to superimposition of two similar progressive waves, either longitudinal or transverse. For example, this is the one wave travelling like this. Here reflection takes place from rigid end. So due to reflection, the wave will travel like this. Y is equivalent to A sin omega t minus kx travelling along the positive x axis. A sin omega t minus kx is moving along the negative x axis. Like that, this is one wave travelling. This is one more wave travelling from same point but downward direction, whose phase difference between these two is equivalent to pi radians. Or this is the free end. One reflection takes place by same wave due to superimposition of these two. Or this is one wave, one more wave travelling from same point but free end, opposite direction. So these are the possibilities of the formation of stationary waves. So one wave can be, in this case, y is equivalent to A sin omega t plus kx moving along the positive x axis. So reflection takes place, y is equivalent to A sin omega t minus k into minus x plus pi, as we discussed earlier. Superimposition of those two forms one wave. Like that, in these four ways of superimposition of standing waves, we will obtain the four general form of standing wave equations. Those are, one is y is equivalent to 2a cos kx sin omega t due to reflection from free end. Similarly, one more 2a cos kx cos omega t, 2a sin kx sin omega t, y is equal to minus 2a sin kx cos omega. These are the four possibilities of the formation of standing wave equation. Let us see one problem based upon the concept of standing waves. In a stationary wave, length of segment is 1.5. Segment, loop, both are same, whose distance is equivalent to lambda by 2, which is given as 1.5 meters. So this is nothing but a 1.5 meters is nothing but a length of the segment, which is lambda by 2 value 1.5 meters. From this one, lambda is equivalent to 3 meters. Now amplitude at the center of the segment is 4 mm. Amplitude the center of segment means maximum amplitude. So this is called as A. So here A is equivalent to 4 millimeters. Again, find the distance between the 2 points where displacement amplitude is 2 mm. That means, so we know AS is equal to A sin kx. AS means amplitude of the stationary wave at that particular point. So this is the point, these are the 2 points, P and Q are the 2 points which are having displacement amplitudes as 2 mm. This one is 2 mm, this is a 2 mm. Now in the problem what he is asking? He is asking us to find out the distance between P and Q. These are the 2 points whose displacements amplitudes are equal 2 mm, 2 mm. He is asking us to find out the distance between them. For that, this is a fixed end. So here we know the formula for amplitude of the stationary wave for a fixed end is A sin kx. A value 2, that already given the problem. A is the maximum amplitude 4. So using this sin kx value 1 by 2, k means 2 pi by lambda into x is equal to pi by 6, x value lambda by 12. Lambda value already given the problem is 3, because length of loop is equal to one segment which is equivalent to 1.5, lambda is equal to 3 meters. Using that value, lambda value 3 meters, 3 by 12, 1 by 4. 1 by 4 means, that means the distance from node to a point P is 1 by 4 meter. Similarly, this is the node to a point Q, also 1 by 4 meter. The total length is 3 meters. From that 3, we have to subtract this distance and this distance. That is 1 by 4 plus 1 by 4 is 1 by 2. The distance between PQ is equivalent to total length from node to node is here 1.5 he gave in the problem, minus 1 by 4 plus 1 by 4 become 1 by 2, which is 0.5, which is nothing but a 1 meter. Therefore, the distance between the 2 points whose displacement amplitudes are 2 millimeters is 1 meter. So this type of model they may ask in the exam. Let us see one more problem of, in the stationary wave, wavelength of progressive wave is lambda. There is an antinode at x is equal to 0, means free end. Ratio of amplitudes at x is equal to lambda by 12 and x is equal to lambda by 8. So here this is free end, means at x is equal to 0 antinode is formed, he gave in the problem. So from here at a distance of lambda by 12 we have to find the displacement amplitude. At a distance of lambda by 8 from x is equal to 0 we have to find displacement amplitude is equal to A2. A1 A2 ratio is asking us to calculate. So we know that A is equivalent to AS, amplitude of stationary wave is equal to A cos x, because it is a free end. So we want to find the ratio of the displacement amplitude. Now at x is equivalent to lambda by 12, A1 is equivalent to A cos 2 pi by lambda into x value. X is equivalent to lambda by 12. Similarly, at x is equivalent to lambda by 8, so A2 is equivalent to A cos 2 pi by lambda into, in place of x we should take now lambda by 8. So here he is asking us to find the ratio of them. A1 by A2 is equivalent to AA gets cancelled, lambda gets cancelled here, 2 goes 6 times, so cos pi by 6 by lambda gets cancelled, here 2 goes 4 times, cos pi by 4, cos pi by 6 is cos 30 value, that is root 3 by 2, cos 45 is 1 by root 2, The simplification of this is our answer. So, root 6 by 2. Mode of vibration such string. A string of length L is fixed between two rigid supports or two rigid ends. It is a plugged center, it is a plugged at its center, then it will vibrate with one loop. This is called, the frequency in the string is what we call first harmonic or fundamental mode, we can say. See, we have to plug the wire at what distance? We have one formula L by 2P. That means where P is the number of loops. If you plug the wire, suppose if P is equivalent to 1, therefore L by 2. Means in order to vibrate with this loop by one segment, it has to plug at the center. Means if you plug middle, that means at a distance of L by 2 from one end. If you plug the string at a distance of L by 2 from one end, then this vibrate with one loop. This is called first mode of vibration. So here L is equivalent to lambda by 2. From this one, lambda is equivalent to 2L. Our aim is to find the frequency. So N is equivalent to V by lambda. So V by lambda is equivalent to 2L. Therefore N is equal to V by 2L. This is the formula for fundamental frequency of such a string when it is vibrating with one loop. Okay. Now same string, it is plugged at a point such a way that it is vibrating with two loops or two segments. So in this case what happens, where we have to plug the wire at a distance of, we have the formula L by 2P, P is equivalent to 2, L by 4. So we have to plug the wire at a distance of L by 4 from one end. So it vibrates with two loops. Then the same length of segment, length of the string is equals to lambda. This is node, this is node, this is node. Node to node is lambda by 2. This node to this node is lambda by 2. Lambda by 2 plus lambda by 2, 2 lambda by 2. From this one, lambda is equivalent to 2L by 2. We want to find the frequency. N1 is equivalent to V by lambda, 2L by 2. Nothing but a 2 times of V by 2L, which is equivalent to 2N. That means frequency of second harmonic is twice that of the fundamental. Similarly, same string, if it is vibrating with 3 segments, in this case what happens, L is equivalent to lambda by 2, lambda by 2, lambda by 2, become 3 lambda by 2. From this one, lambda is equivalent to 2L by 3. Again frequency N2 is equivalent to V by 2L by 3. So which is equivalent to 3 times of V by 2L is equivalent to 3N. Therefore, the frequency ratio, this is called fundamental or first harmonic. This mode of vibration is what we call second harmonic or first overtone. What do you mean by overtone? Overtones are nothing but a frequencies higher than fundamental are called as overtones. So here this is fundamental frequency, this is called second harmonic or first overtone, this is called third harmonic or second overtone. Now the frequency ratio N is to N1 is to N2 is to so on. N is called fundamental harmonic or first fundamental frequency. This is called second harmonic, this is called third harmonic. So harmonic number always lesser by 1 with the overtone number. In this case, overtone number always lesser by 1 with the harmonic number. Harmonic number always greater by 1 with the overtone number. That means 10 overtones we have. So how many harmonics? 11 harmonics. I understood. N harmonics, I repeat, N harmonics, N minus 1 overtones, N overtones, N plus 1 harmonics. So 10 harmonics means 9 overtones, 10 overtones means 11 harmonics. So like that, N, N1, N2, this is fundamental frequency or first harmonic, second harmonic, third harmonic. This is called as first overtone, second overtone, third overtone, etc. The ratio of them is how much here? V by 2L, 2V by 2L, 3 by 2L. Therefore, N is to 2N is to 3N. Therefore, the ratio of the harmonics are 1 is to 2 is to 3. Ratio of overtones, what I told you, overtones are higher than fundamental. Therefore, 2N, 3N, 4N. 2n is the frequency of first overtone, 3n is the frequency of second overtone. Therefore, the ratio 2:3:4. Now, position of nodes. So, this is called node and this is called node. So, here in the two harmonics, node, node, node. In this case, this is node, this is node, this is node, this is node. So, node positions are x is equal to 0 in the beginning, fixed point always node, free end always antinode. 0, L by P, 2L by P, 3L by P, where P is the number of loops. Similarly, position of antinodes. So, from here to here, this is node, this antinode, node to antinode lambda by 4. Similarly, x is equal to L by 2P, 3L by 2P, 5L by 2P, where P is the number of loops over here. These are the distances of the antinodes from the rigid support. So, general formula for frequency n is equivalent to P by 2L under root of T by mu, where P is the number of loops, L is the length of the string, T is the tension, mu is the linear mass. So, here we have loss of frequency n proportional to 1 by L. This is called law of lengths. Second one is n proportional to root T, law of tensions, n proportional 1 by root mu, law of linear masses. So, from this one n1 by n2 is equivalent to L2 by L1, and from this one n1 by n2 is root T1 by T2, so which is also equivalent to root of mu2 by mu1. See here, delta n by n into 100 percentage change in frequency is equivalent to minus delta L by L into 100 only when T and mu are constant, is equivalent to 1 by 2 times of delta T by T into 100 when L comma mu are constant, which is equal minus 1 by 2 times of delta mu by mu into 100 when the tension T and number L is constant. These formulae applicable only for less than 5% of change. Reflection from the free end. So, this is the rigid support, means what you call node will form, free end antinode will form. From here to here, L is equals lambda by 4 in the first mode. In the second mode of vibration, so this is node, this is node, this is antinode, node to node lambda by 2, from here to here lambda by 4, on the whole 3 lambda by 4. So, node, 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 on the whole distance is 5 lambda by 4. This is fundamental, this is called second, what you call third harmonic, this is called fifth harmonic. So, here the frequency ratio 1:3:5. Now, in this case frequency ratio is 1:3:5. Now, for a composite string, means one is these are two strings which are having different mu's are joined together. So, here this is the fixed point, this is the common point, maybe node or antinode. In this case, if it is a node, from here to here, this is one length, one string of length L1, second string of length L2, whose linear mass is mu1, mu2. In this case, the lowest common fundamental frequency, very important formula, Fc is equal to N1 F1 is equal to N2 F2, where N1 N2 number of loops, F1 F2 their frequencies. A string fixed at both the ends has consecutive standing modes. Consecutive means maybe n plus 1 or n minus 1, for which the distance between two adjacent nodes is 18 and 16 centimeters. More length, 18 centimeters more length, less number of loops, less length, more number of loops. So, here let us consider one of the loop length is 18 centimeters. The total length of string will become L is equals to n into lambda by 2, which is L is equals to lambda by 2 18n. In the consecutive mode, as the length is lambda by 2 value is 16, so lambda by 2 less, so number of loops are more. Consecutive means n plus 1. So, now same length of string n plus 1 into lambda by 2, n plus 1 is here lambda by 16, equation 2. For both the strings, length is same over here. So, equating 1 and 2, we got n is equal to 8. So, 8 number of loops are formed in this one. So, therefore, to find the length of the string, L is equal to 18n, 18 into 8, or using this one here 16 into 9. So, therefore, 144 cm is the length of the string. This is a string, one end is fixed, other end is connected to a load. When this is in air, it vibrates with 8 loops. If it is inside the liquid or water, which will be 10 loops. He is asking us to find out the specific gravity of the material of load. We know that n is equal to P by 2 root T by mu. So, 8 loops are formed in air, 8 by 2 root T by mu. Same string, if it is kept inside the liquid, vibrates with 10 loops. So, n dash is 10 by 2 root T by mu into 1 minus 1 by s, because when it is inside the liquid, no buoyancy force comes into play. In the last class we discussed, so that value become 1 minus 1 by s. So, if you divide these two, he said frequency is same. When it is vibrating in two different media, frequency does not alter. So, frequency is same. So equating 1 and 2, 8 by 10 is equal to 1 by 1 minus 1 by s under root. Simplification of this, s is equal to 25 by 9. A rod of PQ of length L is hung from two identical wires. These two wires are identical. A block of mass small m is hung at a point R of the rod. The value of x, he is asking us to find the distance of the load where it is attached from this end, so that the first wire is in fundamental mode, it is vibrating, the second wire with first overtone. See, this is here one loop is formed, here two loops are formed. The frequency of the first wire is F1, frequency of second string is F2. Therefore, F1 is equivalent to 2F2 as given the problem. So, we know F is equal to 1 by 2L, generally P by root 2 by mu, root 2 by mu. So, 1 by 2 root of T1 by mu is equal to 2 by 2 root of T2 by mu. From this one, T1 by T2 is equivalent to 4, and the load M is attached at a distance of x from the end of the P. Therefore, according to moments law, the tension T1 into this distance is equivalent to x, which is equivalent to T2 is acting over here at a distance of this whole length is L. So, this could become L minus x, therefore, into L minus x. Clockwise moments is equal anti-clockwise moments based on that. So, from this T1 by T2 is equivalent to L minus x by x, equation 2. So, from equation 1 and 2, T1 by T2 is equal to 4, replace this with 4. So, 4 is equals to L minus x by x, which is L by x minus 1. From this L by x is equivalent to 5, x is equivalent to L by 5, means we have to place the block of mass m at a distance of L by 5 from the end P, so that this is in equilibrium.